Okay, so today we are covering lesson 4.4. The title of this lesson is Graphing Polynomial Functions. Actually, the graphing of these, where we will actually be doing the graphing, that's going to happen later. This is kind of a lesson to set up how those graphs are going to be done. There are some things that we need to be able to do, some things that we should be able to identify that will help when the actual graphing process takes place next week. So for today, some of this is going to be review, I think. There's really two main objectives. There's four different types of problems on this assignment. I'm going to give you some examples of each type. So what does it mean to evaluate polynomial functions? We're going to talk about that. And then later, given certain graphs, can we identify general shapes of graphs of polynomial functions? That's really the takeaway from today's lesson. So your first type of problem will be presented to you in problems 15 to 22 of the assignment. So as you can see, in this first type of problem, we are to state the degree and leading coefficient of each polynomial. Now, I guess we need to remember whether or not these do represent polynomials. That's a review of a previous lesson. If they do represent a polynomial, then we need to understand what the degree means, how do we find it, and what does this leading coefficient refer to. Well, first of all, let's take a look and see if we remember whether or not these expressions represent polynomials. Well, you can think of these like this. These should be monomials that are connected with plus or minus signs. So if they truly are monomials, then certain things have to be true. The exponent for variables has to be a positive, we'll call it a positive integer. Okay, remember that the integers do not contain fractions. And positive means that obviously they can't be negative exponents. So with that said, that's going to be the main thing that you're looking for as to whether or not these represent polynomials. Letter A does represent a polynomial. So since it does, I'm ready to state the degree. One thing that I would caution you with is make sure that your polynomial is what we call standard form. Standard form means that the highest exponent for the variable should be first. And then you count down in order from there until you finally, the last term, if there is one, should be a constant. So be on the lookout. Make sure that it is in standard form. And if it is, then this highest exponent will be the degree. So the degree of this polynomial is 6. The lead coefficient, remember that word coefficient means a number multiplied times a variable. Lead just means what's the very first one in this polynomial. And the lead coefficient here would just be 5. And that's your complete answer for letter A. Letter B is not a polynomial in one variable. That's the second part of the sentence. If it's not a polynomial in one variable, explain why. Well, the reason why is this last term, if we showed it with an exponent, it would be like this. It would be 4x to the negative 1. And to be a polynomial, it has to have a positive integer exponent. You can say something like this. The last term has a negative exponent. Another way of saying that is you can't have any variables in the denominator, which is what would happen if it's raised to a negative exponent. So anything like that description. Spell it out. Okay, letter C is one that will trick you if you're not careful, because as this is given, it's not in standard form. This would be the standard form. I start with the highest exponent, then I go down to the next highest, then I go down to the next, until finally I have constants. And last, this is a polynomial because all of my exponents of variables are positive integers. So the degree, again, would be 6. That's the highest exponent. The lead coefficient, the very first coefficient, is -1. Okay, letter D. This is not a polynomial in one variable, obviously, because I have two variables. We'll just say it like this. It's not a polynomial in one variable. And if it's not, then you don't have to worry about the degree or the lead coefficient. So I think you'll probably breeze through 15 through 22 with just a couple of heads up items. Again, just make sure that you're looking at standard form before you start looking at degree and lead coefficient, and then understand whether or not you're actually dealing with a polynomial. So any questions on any of that? Any questions? Okay. The next type of problem, and you will want a calculator for this, so if you need a calculator, let's go ahead and take care of that. Okay, what we're doing here is evaluating functions, or a particular function, given inputs. We actually did this with function cornhole, if you remember. So what this means is, for the W function that's provided, what is the output if we let x, in both of these cases, both of the x's, become 5? So literally, this is what I'm going to do to get the answer to, this reads W of 5. What is the value of the W function if I input 5 in for x? So let's see. 5 cubed is 125 times -2, -250, plus 15 minus 12, -235 minus 12, -247. So that would be my answer to W of 5. It's an exercise in inputs and outputs. Now, looking ahead to when we do the graphing, what have we just found on the graph? Anybody know? For this particular graph, what did we just find? Sure. Well, we found for a given x, yes. So in other words, we found one of the points. The point 5, -247, should be on this graph. Now that's not something you have to do today, but I'm just trying to get you to make sense a little bit of where's this going for future. And we're just trying to find some points so we can connect them and see what the graph looks like. Letter B, oh, it's a two-part answer. We found W of 5. Now let's find W of -4. So do the same thing. You're going to input -4 into that function. And you can literally let your calculator do the work on these. You can do all of that just all the way across on one line. Let's see, 128 minus 12 is 116 minus 12, 104. So those are our two answers. So take a moment, maybe a minute at the most, and see if you can come up with the two answers for part B. Find W of 5. We'll see what you get. and then W of negative 4. For those two inputs, what are the resulting outputs? Okay, Colin, what'd you get for W of 5? Very good. You got 698? Nice. All right. And Whitney, W of negative 4? 896. Who got that? Okay, very good. Any questions? So 6 of those that look pretty much just like this. Given a certain number as an input, you find the output. Now the next type of problem is similar, but it's different in that now the input is not just going to be a number. It's going to be an expression that contains a variable. And for some people, this is a little bit weird. So let me make sure you understand. I got 4 of these examples. You're going to do the same thing on 29 through 34. Given these two functions, this C function and this D function, letter A says, let's evaluate the C function if we input y cubed. So everywhere in the C function where we see x, we're going to replace it with y cubed. So it'll look like this. C of y cubed will be 4 times y cubed cubed. I just replaced x with y to the third in the function. Over here I'm going to do the same thing. Where I see x, I'm going to replace it with y cubed. And the squared is part of the function, plus 2. So we just have to remember our exponent property that says when one power is raised to another power. Let's see, Hannah, what do I do? What does that property say when one power is raised to another? What do I do with those exponents? Multiply. So this becomes 4y to the 9th. Same property is being used here. This is going to become 5 minus 5y to the 6th plus 2. So the answer for input y cubed will be this output. So it's actually going to be a polynomial answer. Okay, let's talk about what letter B is asking for. This time we're going to go to the D function, which is here. We're first going to input 2a. So wherever we see x in this function, let's replace x with 2a. Let's do that part first. So 3 times 2a squared plus 6 times 2a minus 10. And we'll simplify this. We have this product being raised to a power. We've talked about that property. So I'm going to go ahead and just do it one step at a time. This product raised to the second power would be 4a squared. I'm just going to do one step at a time. Now I'm going to multiply here. 3 times 4a squared is 12a squared. And then 6 times 2a is 12a minus 10. And that takes care of the part that says d of 2a. Well, all this says is take that result and multiply it by 5. Or in other words, distribute 5 to your result to get your final answer. So 5 times 12 is 60a squared. 5 times 12 again, 60a minus 50. And that is your answer for letter B. Any questions? No questions? Okay, let's try another one. Now we're going back to the C function. This says literally, what is C of 2a? Or evaluate this function called C, letting 2a replace the x's. Let's see what comes out. So C of 2a would be 4 times 2a raised to the third minus 5 times 2a squared plus 2. And now we simplify. The product 2a being raised to the third, that's 8a to the third. The product 2a raised to the second, that's 4a squared. Now I'm going to multiply. 4 times 8 is 32a cubed. 5 times 4 is 20a squared. And there are no like terms, of course, so that ends up being my final answer. Evaluating the c function for a value of 2a, an input of 2a. And one more. Now I'm going to go back to the d function. And this time, in place of these two x's, I'm going to replace both of them with this binomial 4y minus 3. So d of 4y minus 3 looks like this. In place of x, put 4y minus 3 squared. 6, 4y minus 3. And then don't forget minus 10. If you don't want to write this down twice and use FOIL, it means to multiply 4y minus 3 times itself. This is an option. Maybe you've seen this before. We can do a 3-step mental math process. Because, based on what we've learned previously about Pascal's triangle and the binomial theorem, when we expand a binomial, how many terms should we expect in the expansion? For example, this is to the second power, so when I'm done expanding, how many terms should I end up with? 3. There will always be one more term than whatever this exponent says. So for those of you who are tempted to say that this is 16y squared plus 9, anybody tempted? You need to resist because we're supposed to end up with 3 terms after we expand this. So here's how you can do it without FOIL. Square the first term. What is 4y raised to the second power? 16y squared. Okay. Now let's get the middle term. We're going to multiply these together. 4y times negative 3. What's that? If I multiplied 4y times negative 3, I would get negative 12y. Now double that. Negative 24y. We just got the middle term. Now square the last term. Negative 3 squared. Positive 9. Now if you don't like that, if you would rather write 4y minus 3 twice and use FOIL, that's okay. But you should get what we just wrote there. Because that's what this means. Just multiply 4y minus 3 times itself, and you should end up with this. But that's just a way to square a binomial without having to use FOIL. Okay, so over here, 6 times 4y is 24y. 6 times negative 3 is negative 18. And then bring down the minus 10. Let's multiply. 3 times 16, 48. Y squared. 3 times negative 24 is negative 72. Y. 3 times 9, 27. Bring these down. And let's combine like terms. There's only one quadratic term, 48y squared. Let's combine the linear terms. Can somebody give me the combination of negative 72y plus 24y? If you put those together, Casey, what is that? Negative 48y. Good. So we're done with the y terms. I'll mark those out. And now all that's left are constants. 27 minus 18 minus 10. 27 minus 18 is 9. 9 minus 10 is negative 1. So this should be our final, that's our output if we input 4y minus 3 into the d function. Any questions? No questions? Okay, we just have one more type of problem to cover, and then you're ready to practice this assignment. You're going to get 6 graphs. They're going to be provided for you. They look like this. And for each one, you've got three answers to come up with. And letter A is a review. Remember that? Back in chapter 2, lesson 2.2, I think, we learned how to describe the end behavior. End means what happens to the extreme right end of this function. Where's it going? And what happens to the extreme left. So, in case you forgot, I'll get us started on answer letter A. Here's how we determine or describe end behavior. We say, as x approaches going to the right, we'll say positive infinity. So as we travel to the right on the x-axis, that's another way of saying that, where is f of x going? Is it going forever up, or is it going forever down? Up. So as we travel toward positive infinity on the x, the function f of x is also going toward positive infinity. Well, that takes care of the right side. Now let's do the left side. As x approaches negative infinity, is the function going forever up or down? It's going down. As x approaches negative infinity, the function itself is also approaching negative infinity. That takes care of describing the end behavior. Any questions? That should be a review for you. Questions on that? Okay, part B. You've never seen this before, but this is easy. Let me give you a way of determining, just by looking at a graph, whether or not you're dealing with an odd or an even degree function. Here's how you can tell. Look at the two sides. The right side is going up. The left side is going down. You might say that they are opposites, right? So here's how you can remember. Opposites, odd. We have an odd degree function. If they're headed in opposite directions, one's going up, one's going up, the other one's going down, then you have to have an odd degree function. And then finally, this is a review. What is the number of real zeros? That's just another way of saying how many x-intercepts do we have? How many times does this function cross the x-axis? 1, 2, 3. We have 3 real zeros. And that completes the 3-part answer for example letter A. So let's do letter B. Let me get a helper. Somebody help me with describing the end behavior. I'll get us started. As x approaches positive infinity. Anybody want it? Anybody raise your hand? Take it? Yeah, go ahead. Okay, f of x, or the function, is approaching negative infinity. As we go to the right on the x, we're going down forever on the y. Okay, what about the left side? As x approaches negative infinity. Anybody want that? Somebody else? Call on somebody? You want it? Yeah. Good. F of x is also approaching negative infinity. Okay, letter B. Maggie, do we have an odd degree or an even degree? Even. They're going the same way. They're both going down. And how many real zeros do we have? How many? We don't have any. I'm going to say none. We have some complex zeros, but we don't have any real zeros. So that's the kind of thing you're going to be doing, looking at these 6 graphs, coming up with these 3 answers. The assignment is there. It's provided for you. It's that last slide. If you need any help, let me know.